Hello and welcome to today's webinar. My name is Tyler Reid and I'm the Manufacturing Application Manager here at GoEngineer. Today's topic is going to be a revisit of one we touched upon last year in our injection molding webinar. There's been some updates in the past 6 months, enough to warrant a new webinar, and that's what we're going to cover today. So a little bit of an overview. Like I said, this is an update. So if you haven't watched the first webinar from last year, I recommend watching that after this one. I'm going to try not to overlap what we covered in the other webinar. This is supposed to be an update. 3D printed injection mold inserts has been a hot application in the past year. So 3D IM is what we're calling this, 3D injection molds. And essentially what it is, if you haven't watched the first webinar, it's the printing of injection mold inserts or injection mold tooling. The reason why we do this, it allows us to create quick, fast, cheap prototypes out of true to spec materials. We obviously can print in a lot of different materials, a lot of engineering grade plastics and a lot of acrylic based plastics, but there's many materials that we can't print directly in. Things like polypropylene, polyethylene, POM, any glass filled polymers that we might need parts for different reasons. And so traditionally we've had to go to injection molding for those parts. And now what we're doing is we're using 3D printing alongside injection molding. So in the past 6 months, Stratasys has made some huge leaps in this application. For one, they created a dedicated 3D IM division within their company. This is the only application that I know of that has a dedicated division. They've also partnered with a company called Worrell, which is a product design house in Minneapolis. We'll talk about Worrell in a little bit, and if you watched my webinar on medical industry, you might have heard me mention about Worrell. And then lastly, they've done some testing with another big injection mold house called Nipro Healthcare. They've used Nipro Healthcare to do a lot of their testing for different materials and to figure out what sort of processes work on these printed injection mold inserts. So where's the best fit? Right up front, we're not trying to replace aluminum or steel tooling. Absolutely not. There's a small niche of applications that 3D printed inserts are going to actually work out. First up, it's going to be a short run of parts. I say short run, I mean 1 to 50 parts. Also, a situation where you need a short lead time, 1 to 3 days, we can deliver parts. This is opposed to aluminum or steel tooling where you're talking about a few days at least for aluminum tooling and usually a few weeks for steel tooling. Complex molds. You'll see some molds in this presentation that are fairly complex, and as complexity increases, traditional milling costs go up. With 3D printing, it doesn't matter how complex or how simple the mold is, the cost is the same. So we start to get an advantage the more complex the molds become. Also, anytime you're in a prototyping phase, or where your part is still to be iterated, there's an advantage to going with a 3D printed insert because they're cheaper and the lead time is quicker. We'll look at some specific numbers later on. And so if you're prototyping, you don't want to invest a lot of money into an aluminum tool or especially not a steel tool. And then also there are situations where you absolutely need the true material part, in particular for medical certification and testing. That's the reason why customers are moving over to Worrell for their medical injection mold parts. So that's a quick overview here. The process of injection molding, particularly 3D printed injection molding. We're going to do a mold design. We have to design the mold around the original part. The fundamentals of mold design still apply, but there are some particulars within the design that we're going to talk about more in detail here. Then we're going to 3D print the mold. It's going to be a polyjet process, and you're usually going to use a digital ABS material or a Vero material. We'll talk a little bit more about those. And then you might post-process the mold, meaning you might bead blast it, sand it, or do some sort of coating. And then lastly, you're going to run parts. And you're going to develop a process to make sure that these inserts survive as long as possible. So we're going to go over each one of those steps in a little bit more detail here. Mold design. The first question I would ask myself if I was designing a mold for myself or for a customer is the mold going to be shot on a professional or a consumer level machine? Most of the examples that we look at today are going to be coming from your professional level machine that is anywhere from 30 to 80 tons clamp force. I mentioned a consumer level machine because this injection mold process is actually kind of lends itself to a do-it-yourself type setup or an R&D setup. And there are manual hand press machines out there. We have one here in our office, and I'm going to talk a little bit about that. Some decisions that you make about the mold are actually going to change depending on whether you're on a professional or a consumer machine. All right, so the fundamentals of mold design actually stay true, but there are some particular aspects of the 3D printed mold where if you take them into account in the mold design, you're going to get better life, better durability out of your mold. Because that's the number one concern right now with these 3D printed inserts is the lifespan of the inserts. They don't last nearly as long as even an aluminum insert. So anything that we can do to increase life is good. First off, you're going to oversize your sprue or your edge gate. You're going to do it a little bit larger than what you would normally do in an aluminum tool. You're also only going to use sprue or edge gates. You want to avoid tunnel gates, cashew gates, banana point gates. Any gate that has a high shear stress on the part, you're going to want to avoid. So an example of a tunnel gate, basically it cuts off the runner as the part's ejected. You don't want to do that. And the reason for that is it puts a lot of stress on the mold. We want to maximize draft to help the part release. In the parts that I've done, I haven't added draft unnecessarily, or I haven't added draft beyond what I designed in the part. But if there's room to add draft up to 5 degrees, you can do that. You're going to want to inset shutoff surfaces anywhere from 2 to 4 thousandths. A shutoff surface is a surface where the cavity and the core of the mold touch, and traditionally they touch right at the parting line. But because of the tolerances in our printers, we found that if you inset them slightly so that they overlap a little bit, you get a better part with less flashing. If you're on a professional level machine and you have an ejector system, you're going to use ejector pins just like you do on a traditional tool. We usually want to print those holes undersized and then ream them to size. Also, in some instances, based on the requirements of the part in terms of tolerance, you might need to add inserts. And those inserts could be 3D printed or they could be aluminum inserts. We're going to see examples of both later on. And then lastly, this comes up a lot, the question about water cooling. It's not recommended. We can print internal water channels. That's neat, nifty, but the heat transfer just doesn't work the same way as you would expect inside an aluminum or steel tool. It's not as effective, the heat transfer from the plastic to the water. So we normally just recommend don't deal with the water cooling at all. So we're going to take a quick look at some molds. These next 3 molds came from Worrell, and these are just the inserts. They're about 4 inches square. These are put into a mud box. A mud box is basically a base for the inserts. We'll see a picture of it later on. What I wanted to point out here is we've got some counterbore holes in the corners. Those are to mount the insert to the mud box. We also have some vents in there. They're kind of the really shallow rectangular channels moving away from the deep channel in the center. There's an example right there. There is an insert that goes to the part that looks something like this. So you can see this is an aluminum insert, and there's actually 2 aluminum inserts here. We have an edge gate that's kind of that J-shaped area. We have some locks on the far left and the far right side of the mold. So the 2 halves interlock together. So the reason for this insert is, for one, it's very difficult to have a strong and stiff 3D print of that size. So this insert's quite small. It's a couple inches long, and the diameter couldn't be more than probably 20 thou at the end there. And so we make it out of aluminum because we can create that aluminum insert very easily and maintain tight tolerances. That particular insert is actually called a pick out. And the reason it's called a pick out is it comes out with the part and then it's picked out by hand later on. The secondary aluminum insert up at the top, that plate, is to help align the pin. So you can see it has a little groove in there. The end of that pin sits in the aluminum groove, and that's going to help hold it a little bit tighter. So this is what I'd call a hybrid. This next one is also a hybrid. It's a hybrid. It has 3D printed inserts and aluminum inserts. Okay, so this green material, the base of the main portion of the insert is the digital ABS material. It prints on our Connex machines. The blue inserts that you see are Vero blue material, and these print even on the desktop printers. And the reason why Worrell used these Vero insert is because they hold a little bit tighter tolerance than the digital ABS. So there's kind of a play between materials here. The digital ABS is a high heat material. It's very tough and it's very durable. but it doesn't have quite the tolerance or resolution as the Vero materials, which are a little bit more brittle. And so they kind of use a combination here. They also use the aluminum there, again, for a tight tolerance area. That part is too thin for a 3D printed insert. So the use of these inserts, especially with the aluminum portion, kind of gives you an idea of where you might use 3D printing and where you can't. Just because you need a true to spec part and you need it in 4 days doesn't mean you can use 3D printing for that part. There's limitations to this technology, and that's one thing that we're learning now and we're continuing to learn. All right, so the next step beyond the mold design is the printing of the mold. Like I mentioned, this is a PolyJet process only. So here at GoEngineer, we represent Stratasys machines. Stratasys has two technologies, FDM, which is a thermoplastic extrusion technology, and PolyJet, which is a UV curable photopolymer technology. This is PolyJet only. The reason is, first, when we print in gloss on the PolyJet, we can print at Z layers of 6/10,000ths of an inch. So it's very fine layers. The resolution and the tolerances are better on the PolyJet side. We also print parts that are essentially 100% dense, whereas FDM is a little bit porous. And then also we have the fact that in injection molding, you're always using a thermoplastic polymer to inject into the mold. Since these are thermosets, we don't have an interaction. Where if you try to inject a thermoplastic into a thermoplastic mold, you're going to start to see issues. So digital ABS is the preferred material for longevity of the mold, but we can also print these molds in Vero Blue, Vero White, Vero Clear, and Full Cure 720, but we can expect less life out of the mold. I've been using our Objet 30 Pro and our 30 Prime here in Salt Lake City to print Vero Clear molds so that I can actually see the mold as it fills. Like I said, we want to print in a gloss finish. And just as a tip, if you're actually doing the printing, the orientation can make a difference. We usually want the X direction on the print to be parallel to the polymer flow, if possible. And absolutely, we want to minimize the support material. The reason for that is support material leaves a matte finish on the part. And we don't want matte. We want a nice, smooth, glossy finish. Next step is post-processing. So the post-processing step is optional in most cases. The reason why you would post-process a part would be if you wanted to alter the surface finish on your end part, whatever you're injecting. If you wanted to make the part easier to release. If you're having trouble fitting the insert into the mud box. Or if you want to increase the durability, there's some things that you can do to post-process these. Some of the post-processing steps might be coating the mold. You can coat it in like a high-temp lacquer or mold release if you're having trouble pulling the mold. Mold release is not used very commonly because one of the main practical uses of this technology is for parts going to certification testing or validation in the medical field, and they tend to want to eliminate the mold release from that validation stage. We can also sand these inserts like you see in the image there. You could bead blast it or sandblast it or polish it. That's going to change the surface finish on your final part. And then we might mill some flat surfaces, especially on the back side or on the sides of the insert. If it's a tight fit on the mud box, we might mill some flat surfaces. So here's some examples of some parts that came out of a post-processed insert. All right, so you're looking at 4 different parts, 4 different types of post-processing, and you can see the surface finish is a little bit different in each. So starting at the left, remember, these steps are being done to the mold itself. So the mold was sanded with 600 grit sandpaper. And you can still see some lines in the final part. I think these are polypropylene parts, but still a kind of a glossy finish. The second part was sanded and then polished. The mold was a little bit more dull, matte finish, but more even. The mold in the next step was sanded and then bead blasted. Less dull, more matte, more even finish. And then lastly, we have a mold that was sanded and then polished and then lacquered. And you can see the part pulled some of the lacquer off the mold and gave it a nice gloss finish, very even finish. That's a very good looking part. I think if that part came off a steel tool or an aluminum tool or a 3D printed tool, you wouldn't be able to tell the difference. It's a very good looking part. And you can see these are all untrimmed, so there's a little bit of flashing on there as well. And then the last part you see is a painted part that's been painted after it came off the injection mold machine. You can obviously do that as well. Okay, so the next step in the process after we've designed the mold and printed and post-processed the mold is we're going to run some parts. So this is where we actually are loading the insert into the machine, and we start to develop a process. This is absolutely critical to the mold longevity. So this is what I've seen work in my experience and also what Stratasys has seen in their experience. You want to start with some initial settings that are very conservative. So what they recommend is an injection mold time limit of 20 seconds. You don't want to have that nozzle up against the mold for longer than 20 seconds, injecting material. You're going to do a pack and hold phase of 0 pressure, 0 time. All right, so you're not going to pack and hold this. A shot size, you're actually going to undershoot it to start with. 75% initial setting. A barrel temperature, you're going to want to set it at the low end of whatever plastic you're using recommends, and also an injection speed at the low end, and then a cooling cycle for the part from 40 to 90 seconds. So you're going to start out very conservative, and then you're going to start to ramp that up. You're going to do some trial shots. You're going to increase the shot size. Target is about 90% of what you would normally do. Adjust the packing pressure. So now we're going to start adding packing pressure and time at the end. And your target end goal is 30 to 50% of the injection pressure and increase the hold time. While you're doing this, you absolutely need to monitor the mold temperature. If you start to run parts quickly, one after the other, the temperature of the mold is going to start to gravitate upwards. And as the mold increases in temperature, the durability actually goes down. It becomes more brittle. So to start off each injection, we really want to be around 120 degrees Fahrenheit on the mold. Here in the office, I do this with a heat gun and a laser thermometer. I hit it with the heat gun until I get about 120 degrees, and then I start molding. It is critical that you have a mold temperature above ambient. And the reason for that is if you don't, then you have to use a higher polymer temperature, and you're going to get all sorts of crazy mold characteristics, good chance of short shooting, etc. So monitor the mold temperature. You can do that by increasing the cooling cycle, or you can hit it with compressed air. But again, you want to avoid water cooling. All right, so we're going to look at a few quick case studies. These come from Stratasys. And I wanted to show these because they're kind of real life examples as to what people are doing, and they give some data. All right, so the first case study, if you've come into one of our offices, you may have seen this part. It's a steering wheel connector. And the final part is made from high-density polyethylene. It's a pretty complex part with some thin walls. And what they said is they were able to get 10 parts out of a tool. So some stats on this. Nozzle temperature of 365 degrees. So that's obviously higher than the heat deflection temperature that we list for digital ABS. And that's going to be consistent across the board. Pretty much the lowest temperature you're going to be dealing with injection molding is 350 degrees Fahrenheit. Injection pressure, 8,700 PSI. Hold pressure of 4,300 PSI. So we're injecting that plastic at almost 9,000 PSI. And then once it's full, we're going to hold pressure on that, 4,300 PSI. The two halves of the mold are clamped together at 30 tons. So that's actually on the low end of a professional level machine, 30 tons. 360-second cycle time. So that's part to part, 360 seconds, which is an eternity in injection mold production. But for prototyping, when we're only creating 10 parts, that's no time at all. All right, case study number 2. This is an enclosure with a living hinge. It's got some bosses and then a press fit or a snap fit. This particular part is made from polypropylene. It wasn't particularly demanding. We were able to create 100 parts using 2 different tools. Neither tool failed. All right, so we could have kept producing these parts. The reason for that is the polypropylene has a good flowability and a relatively low melt temperature. So the nozzle temp was a little bit higher on this, 430. Injection pressure and hold pressure relatively the same, a little bit less hold pressure. Cycle time about cut in half, and we had air cooling on this. So that means after the mold was separated, the part itself was hit with an air nozzle, and that helped cut the cooling time and the cycle time. Third case study here, another enclosure. This time it's made of ABS material. Got ribs and bosses and some shutoff surfaces. We talked a little bit about those. The shutoff surfaces, most easily you can see it in the red parts there. It's the circles that are basically holes in the part. Those form a surface where the cavity and the core have to touch. And like I mentioned, when you're designing your mold, you usually want to inset that a little bit, 2 to 4 thousandths. Nozzle temperature 410, injection pressure less this time. Cooling time also less. So the ABS plastic was a great example of a material that you'd want to use, much like the polypropylene. A few more quick case studies. I wanted to give an overview of some of the tooling costs and lead times that we've seen traditional versus 3DP. So I think a lot of people overstate the true cost of an aluminum tool. What I'm seeing here is fairly accurate and fairly in line with what I'm seeing out in the industry. A lot of people like to say aluminum tools are going to cost tens of thousands of dollars, and that's really not the case. You can get aluminum tools within the span of a week for under $2,000. According to Stratasys in their research, the average cost of an aluminum tool is $2,500 to $25,000, so it obviously changes on complexity. All of these are under $2,000, but the digital ABS prints are all a fraction of the cost. So still cheaper, and the lead time's a lot less. So there's benefits in both arenas. So the real advantage here is you might have to cut a mold once, but you also might have to cut a mold 2, 3, 4 different times if you have design mistakes or design changes, if your part is still being iterated. So that might be a perfect example of when you would go to a 3D printed insert because the lead time is very quick and the cost is less. Once you vet out the mold design or once you vet out the final design, then you're going to go to your aluminum or steel tooling for production. And that's where this 3D printed insert fits in. So I wanted to show a couple more photos. These are from Worrell. I took these when I visited them in November. They have an 85-ton Toshiba injection mold machine. This, along with their Connex 3D printer, were the first machines that they invested in. They're a design house. And the reason why they invested in these machines, as they explained it to us, is that they were filling a niche that their customers, who are predominantly medical device companies, needed to fill. And that is true to spec, very quick prototypes in a small number, 10 to 50, to send off to animal testing and to set them up for validation. So that's where these guys kind of excelled. What you're seeing here is this orange part is a test part that they created for this workshop we attended. It's a polypropylene part. In the top left corner, you can see several parts that were run in order, and you can kind of see that process validation happening in those parts. The first part that they ran was in the bottom right-hand corner. You can see it's not quite 100% filled. It's a little bit thin. They were running their machine at lower pressure, little to no packing pressure, and they were purposely short shooting it. As they progressed, they ramped up their specs, and they produced the last part in this series, which is the bottom left, which is very solid color. This is a full fill. It's a very excellent part, polypropylene. Here's some more pictures that I took while I was there. Up in the top left corner, you see what I referenced earlier as a mud box. The mud box is the base where the inserts are placed into. Essentially, you would create one mud box, because that's where a lot of the investment is in this process, that fits several different insert sizes. And then you would design your inserts to fit in whatever mud box you have available. Bottom left-hand corner, you can see the mold inside a mud box, ready to be shot. And the part that came out of that mold is just to the right. It's the part that I'm holding. It's the clear polycarbonate part with the aluminum pick out. That part that I'm holding is one that was in animal testing while I was there, so it may be finished now. That's well on its way to becoming an approved FDA medical device. Moving over to the fork, that was a part that Worrell did for Target, polypropylene forks. Very quick, could deliver really dozens and dozens of parts within 3 days. That's Worrell's promise, 50 parts within 3 days. On the bottom right-hand corner, you can see an example of the insert that produced those orange polypropylene parts. You can see it's got a very deep draw. It has 2 inserts that have kind of slide action that come out of the top. The inserts are missing there, but they create these shutoff surfaces in the part. And they actually didn't have these shutoff surfaces inset. And so if I go back one slide, you can see in the parts up on the upper left, there's a whole area that should be clear, but there's flashing within it. So if they had inset those shut-off surfaces, I would have expected a little bit better on the flashing. Up in the top right-hand corner, you can see the gate on that same mold. And notice it's a white color. That's the white version of that digital ABS, and it's replaceable. So going back to the mold design, I mentioned you want to do sprue or edge gates. And if you really want the most life out of your machine, you're going to make that gate replaceable, because that's the one point that fails most often is the gate. And you might actually create several different ones with a little bit different geometry, because that's going to be the least durable part of your mold. And then in the top center there, what you're looking at is the back side of that same mold that's been blown out. So eventually these molds do fail. This one, I was told, failed around the 3 to 4 dozen mark. Okay, and it blew out the back side. That actually could have been prevented, possibly, because what happens as you're molding these parts, the molds tend to change shape slightly, and they sit a little bit cockeyed in the mud box. And so every once in a while, you're pulling them out and you're shimming them back flat. And what may have happened here is that it was time to shim it and they missed it. It was able to blow out the backside. That's eventually how it's going to fail. All right, the next few pictures are from my experiments here in the basement at GoEngineer. Like I mentioned, we have a little manual, just hand-activated injection mold machine. It came out of a Kickstarter project. The company's called LNS Technologies. It's a pretty nifty little machine. It's got a digital temperature control, goes up to about 500 degrees Fahrenheit. We can shoot 1.25 cubic inches of material, and it costs about $1,500. So if you're in a do-it-yourself or R&D type setting, it's a very small commitment in terms of cost. This was the first mold I created. It's a Vero clear mold, and it's just a little button with our logo on it. You can see the top portion of the mold is damaged. I shot probably 30 different parts out of this, and I was becoming very aggressive with how much pressure I put on the mold and how long I packed on the mold. And because we had a very hot brass nozzle touching the tops of our parts, you know, the brass nozzle in this case is set to 380 on the low end or 470 on the high end for these materials. I have a 470 degree brass nozzle putting pressure on the top of my part for 20 seconds. That's eventually when it failed. So this was my first foray into it. What you're seeing here is polypropylene. That's the green material. And then I worked my way up to Delrin, which is the white material. I didn't do a good job of clearing out my materials. So as I got to the Delrin, I got a little bit of a mixture of polypropylene, the white Delrin, and the black is basically burned polypropylene. But these came out great. The next mold I made was a little bit more intense. I needed to make these little knobs, and the knobs had a stainless steel insert in them. So I created a 3-part mold. You can see on the left there. There's a part with the wings that a screw screws into, and then we place that into the mold, and then we mold around the hex head on the screw. Those little gold inserts that you see that I used, they're heat set threaded inserts. These did not work. So there's these little inserts that we basically heat stake them into the plastic. I use just a soldering iron to press them in, and the heat transfers through the brass into the plastic, melts it, and they press into place. It works great for FDM. This was my first time trying it on the PolyJet stuff. I don't know why I thought it would work, but it didn't. So don't use those for PolyJet stuff. But the mold still came out just fine. Here's some example parts that came out of this mold. These were polypropylene. I injected at 390 degrees Fahrenheit, so a little bit higher than recommended. The reason for that is my molds were cold and I needed good flow around the hex head. Stainless steel insert. So we got a little bit of flashing on that, but overall, that's a great looking part. And it performs just as well as the part that I mimic in terms of twisting it as hard as you can and it doesn't break. So this is of my first mold. You can see here that brass nozzle that I was talking about. Very small surface area. This is shooting a thermoplastic elastomer. Oh, it looks like this is actually of the knob. You can see the clear mold is pretty neat because you can see it filling. You can also see when I'm overfilled, start to get flashing at the runner. So I pulled that out. Now, if I wasn't filming this, I would have let that sit for probably 30 seconds to a minute to help it cool. But because I was recording this, I started to unscrew it immediately. One of the reasons why we have to let it cool for a little bit longer is because of the heat transfer issue we talked about. The heat from the plastic doesn't transfer to the mold as well as it normally would. So overall, in the span of a minute, we had a part on the knob. The last little project here, I finished this up yesterday. This is called a beanie band molly. This is made out of thermoplastic elastomer, so kind of like a rubber-like material. This is a very complex part. This is a part of one of our customers that we got permission to create a mold of. I saw this part. I instantly wanted to create a mold of it because look how complicated those two mold halves are. This part here is about 1 1/8 cubic inches. And once I added the sprues, the sprue and the gates, we were right at that 1.25 inch limit for our machine. So it took a full stroke, but it actually worked pretty well. Take a closer look at these. These parts, I took these pictures with my phone. These came right off the machine. There's no trimming of any flashing on there. Look at the detail. These parts are about 3 inches wide, so fairly small. We see some details on the lettering on the top half. That top surface looks great, nice and shiny. The bottom surface, we've got these little nubs. They help create friction on this part. The way this part's used is it's strapped to a helmet or strapped to a beanie, 3 of them, and then you can place sticks or twigs in there to help camouflage. So this is used by hunters and servicemen. So it needed to be a durable part. This is a part that we prototyped in a traditional way. We printed it, and because this part is strapped down, it's tugged and twisted, our 3D print eventually failed. I wouldn't expect this part to fail easily at all. It's very robust rubber. The total cost on this mold in terms of material is in the hundreds of dollars. The person who originally got this mold cut, he was up around the $2,000 mark for this mold, and 1 to 2 weeks delivery time, where I did this whole project in the span of a day and a half. So that about covers what I had prepared for you guys. Again, this is an update on an earlier webinar, so if you were a little bit lost, maybe go check that earlier one out. Hopefully that will clear up any questions. If not, feel free to reach out to me. My email address is there. I also respond to YouTube comments, or you can add me on LinkedIn. And I want to thank you guys for joining us on this webinar. We're going to be doing another 3D printing webinar 2 weeks from today, and we're going to be doing 3D printing webinars every 2 weeks this entire year. So we have lots of content coming towards you guys. Thank you for joining.